Good day, everybody. Hey, we're going to start exactly at 11 o'clock, so we're going to wait for a few more people to get on board, and then we're going to start the presentation. Thank you.
Good morning. Thank you all for coming to our Hydropower webinar. I am your moderator, Christine. Today, our mechanical seals expert, John Sousa, will discuss applying advanced main shaft seal technology to improve turbine reliability. John has worked at A.W. Chesterton Company for over 30 years and has a strong business and technical background. Over the past 15 years, he has worked in marketing and has been the project manager responsible for all split mechanical seal development and other mechanical seal products. He led the redesign of the market-leading 442 split mechanical seal and was instrumental in expanding split mechanical seal capabilities for various equipment and operational scope, developing size capabilities for large rotating equipment and for hydropower water turbine main shaft sealing. If you have any questions, please feel free to type them in the chat or questions box, and we'll address them at the end. If you like what you see and hear today, please join us again next week when we discuss sealing for Kaplan turbines. And I'll put that link for registration right in the chat box. And I'm going to turn it over to John.
Thank you, Christine. Good morning, everybody. Hey, thank you.
Go ahead.
We manufacture all these different products, mechanical seals, packings that we also use for sealing turbines, polymer seals for Kaplan blades and other things, composite coatings that we rebuild turbines with. And today we're going to talk about mechanical split seals. Split mechanical seals is what we're going to cover. All right, so we have some goals that we want to cover within this half hour. You see the picture there. That is a turbine seal, main shaft turbine seal that failed. All right, it's on the side of a turbine. You know, we know that the seal failed because it's there, and it's all in part. What made it fail? Was it a system issue, or was it a design issue of the seal? So when you look at trying to determine the best sealant solution for your turbine shafts, you know, you need some information to make that decision. So today, what we're going to try to do is identify, you know, briefly turbine system variables that affect sealant reliability. We're going to review the technological differences in main shaft sealant systems. We're going to look at factors affecting seal reliability. Look at, you know, how much leakage is acceptable. All right, so you know, most of your turbine seals leak, and they're designed to leak, so you're not familiar with sealing devices that don't leak. We're going to look at environmental controls and their role in sealing turbine systems. And we have a few illustrative case histories and applications that we want to show you just to, you know, make it easier to comprehend what we mean about what we're saying here. Okay? So when you look at, you know, turbines, you have all different types of turbines. They're all different size shafts. Okay, they have all, you know, varying requirements for sealing systems. Shaft speeds, 45 to 1500 RPM. You have all different types of speeds. Pressures that the seals see are all different. Typically, you pump in river water, but you know, the quality of the water is obviously different, predicated on, you know, what the source of the water, the river water is. Temperature is usually not an issue, right? So it's typically ambient, seasonal. It could be hotter or colder over the year. The systems may pull a vacuum and sometimes run dry. So how do you protect against that stuff? Your solids contents from your river water varies seasonally and by source. Cavitation can occur when your water level of your turbine changes. You have conditions at startup, all right? So some turbines will lift off and you'll have shaft movement, and you have to be able to deal with that. In special pump storage operations, you have reversing. So you're going to have, you know, you got to go clockwise and then counterclockwise to, pump the water up and then generate the electricity as it comes down. So, basically, when you look at your system, the turbine type and orientation will predicate what you can or cannot do in terms of seal selection or, seal use. Your shaft size or your sleeve size is important. So, typically here, we all have split seals. Whatever technology you use has to be split. The speed is important because that generates the heat that's associated with the operation of this seal. Pressure is important because it'll have an effect on, the sealing device and what materials you can or cannot use. Startup conditions, as we always talked about, water sediment content, water filtration capabilities and limitations. A lot of times we see issues with just the filtration aspect of it. So if I need fine filtered water to make my seal operate, how do I get the amount of water that I need and the, eliminate the solids in there? We run into environmental problems, oil leakage going into, rivers, etc. Leakage control, because most of these devices do leak. When they start to fail, the leakage increases, and typically you have some pumps that pump out the water to the river or wherever you resource it. That has to happen. And the turbine condition, what's the run out and the axial movement of the turbine itself. So all these things here, the conditions of your equipment, will affect your reliability and what you have for choices in seals. So, what are end users looking for? All right, so this is like utopian. So I want long seal life. I don't want any leakage. I want to minimize my flush. I don't want any adjustments to the pack-in or whatever sealing device that I have. I got to make sure that the seal doesn't have any catastrophic failure. We're looking at, we don't want to wear a shaft or sleeve because that'll accelerate leakage, and then it'll make when I have a down period, I got to replace the sleeve to make the sealing device work. We want to make sure that the seal's easy to install, okay, and dismantle. All right. We want quick installation. We want, we don't need 20 MIT engineers to install the seal. Components that fit the shaft. Simple design. All right. So we always like to look at KISS, keep it simple. Stupid, in service. So, you're not going to have expertise in everything. So you need a partner who has, service capabilities to assist not only in advising in terms of what the seal selection should be, but also to install the seal. And safety is utmost in terms of operating these systems. So there are a lot of sealant technologies available. We're going to key in on split mechanical seals. All right. It's the newest innovative technology for main shaft sealing because it's an axial seal. There's no sleeve wear. They're designed not to leak, predicated on the condition of the turbine, the installation, etc. You may get some leakage, but it's very minor compared to what you see with the other types of designs. And what we try to do is to reduce or eliminate flush requirements to make the system more reliable. So again, we need to understand what you have for equipment and what your issues are so that we can look at it and make recommendations to enhance your reliability. People are familiar with segmented axial seals, segmented radial. Because the equipment's big, you need to have something split. So you have different technologies to achieve that. Polymer radial, polymer type seals that seal on the shaft, and compression packing, which we also make here. All right, so when we talk about radial versus axial sealing, What we mean by that is that radial sealing, the dynamic seal seals on the radial aspect of the rotating shaft. So it would seal right here, okay? So it's going to press against the actual shaft, and the dynamic seal is between the sealing device and the shaft. The shaft sleeve wears increase in leakage, and you do need leakage for, all these types of radial sealing devices. And a particular issue that we see in the hydropower turbine business is that you have silt and sand, and typically with with these materials that are running against the shaft, they have to be softer materials than the shaft itself, okay, and they have to be somewhat compressible. So predicated on the properties of the materials, if your sand or silt come through your runner and they embed into the sealing device, it's going to act like sandpaper, and it's going to wear the shaft, wear the sealing device, and increase your leakage. Now, axial sealing, your seal is in the direction of the axis, okay, of the actual shaft, and the dynamic sealing elements are perpendicular to the shaft, and they're part of the seal. All right, so you don't have any shaft wear when it comes down to most axial sealing types, predicated on what secondary materials they use for sealing. So the wear occurs between the sealing elements, and it's incumbent upon the manufacturer to design the seal so that you maximize the operating conditions of the sealing device. All right, and that's where the axial is, that way. Okay, so for typical radial sealing devices, on the left you have a packing device, and on the right-hand side you have like a elastomeric type seal. So with radial sealing, the seal sits on the radial aspect of the rotating shaft. All right, so those red lines that I'm throwing in here, that's where they seal. So they seal right against the shaft. Okay, they all require fine filtered water to cool or lubricate. All right, so we're talking typically 5 to 10 micron, predicated on the design of the radial seal. They all need to leak to operate at different amounts. Your flush pressure, all right, the pressure of the flush water, seeing that you need leakage, you're going to have to ensure that your fine filtered flush is flushed into the system, through their ports, so here, coming through here, or through here, so that it lubricates and cools the sealing device. So if I'm rubbing material against the shaft, all right, I need to make it close tolerance. So it has to, hit the shaft, and everything's not particularly concentric. So you're going to have some motion there that's going to, affect the sealing and also wear the shaft and the sealing device. So all those things have to be considered when you are, choosing a sealing device. And typically when you look at it for the hydropower industry, as opposed to other industries, leakage control, you're really trying to control your leakage. You're really not trying to seal it. So, basically, those are your options. All right, and it will wear the turbine shaft. So the reasons that people use radial sealing devices is that typically they're low cost. Replacement cost is typically low. People have used these over centuries or decades, right? So you're familiar with how you seal with pack-in or other types of these devices. And you basically have short lead time. You're taking a packing piece and you're cutting it to the size and you're installing it into your turbine. So basically how they work, all right, and this is all types of radial seals, that you put your sealing device, in this instance it's packing, into the stuffing box. You have a gland that exerts pressure against it right here. So this plate is screwed in, and it forces the pack-in into the chamber, and it seals it axially and radially, and it seals here. So what happens is that you need the flush water here to make sure that the seal is cool and lubricated, because you are generating a lot of heat, right? So you're running two items at a certain speed with a certain circumference. You need to cool it, right? Your flush pressure has to be greater than your runner pressure, the water coming up from the runner area. If the runner pressure is greater than the flush pressure, the river water is forced into the stuffing box, okay? That brings in particulate, which will embed into the packing, and it'll enhance accelerate the wear of the packing in the shaft, which will increase your leakage rates. It'll also, you know, it's the same for any type of composite or polymer. So the material has to be, you know, such that it's typically softer than the shaft that you have. All right, on the axial side, you're actually sealing, you know, against the two faces that are part of the seal. All right, so here on a segmented, you have these segmented sealing surface. So you're trying to go around the circumference of the turbine area with these puzzle pieces, okay? And everywhere where you have like a segment, you have a leak pad, okay? The other thing is that you want the faces to be flat, right? So you want to have a flat surface so that the other seal ring sits on it, you know, snug, and you don't have a big gap that will have capability of leaking. So these are the issues that you have with segmented seals. You need the flush water, okay? You can't get sand and silt between the segments and between the faces and everywhere else. So you need to flush. You need to have sufficient flush to overcome whatever the operating leakage is, and also, you know, your pressure requirements, and you know, you need to be able to control that. So, you know, sealing elements are typically carbon, a polymer. Sometimes you have metal. You know, like you might have a hardened seal at the best, or, you know, other types of metals that they use. But, you know, you got to look at your leakage and understand if your system is going to be able to handle the amount of flush that you need to operate the sealing device long term. So basically, I was at a hydropower station a few months ago, and when I came around the corner, I saw this big old pump outside. I was wondering what it was. So when I went into the facility, I noticed that they were they had a sump pump that was pulling the leakage, the seal leakage, from a sump area outside into the river. All right, so that was one about 11 megawatt unit that was leaking this amount of water 24/7. All right, so, you know, what can you do to minimize your flush requirements? So basically, your design, I mean, you have your turbine design, your system design, and operating conditions. All right, so what do? You know, your water conditions are going to be variable. Flush water availability. Usually, you're in remote locations. You don't have, you know, clean city water to flush your seals with. Your seal's going to have flush requirements, right? Filtration requirements, as I mentioned, 5 microns, 10 microns. Your head pressure will also have an effect on your leakage and what you need for water filtration. The seal design, the materials of construction, you know, the type of design, heat transfer properties of the materials, the thermal properties, you know, if I'm using an elastomer, what's the growth? You know, what's the elasticity? So if my seal surface is, you know, where I'm sealing moves, okay, and is not flat, I'm going to have potential leak areas. Centrifugal force, all these seals are split. You know, with a packing set, it's not a big deal, but when you're talking the axial sealing devices and, you know, certain designs, you know, you have to understand, the speed and with the effect of the seal it's going to have on it. And the design leak paths, like we mentioned with the segmented seals. All those seals are designed so that they can get around the shaft, but you have all those leak paths. All right, so here's a slide that goes over some people's seal designs and the amount of water that you see going through your systems. So I'm not going to get too caught up in this here, but one of the seal is using 4.2 million gallons of water per year. All that water has to be filtrated, right? And if you have to filtrate it at 5 micron, that's a lot of cost. Okay, not only is it cost, is the reliability of the seal to have the filtered water 24/7 and operate in whatever filtration device that you use that may have automatic cleaners, etc., and you'll have pressure variations within the system. All that has to be accounted for, right? So you need to understand your system before you pick your sealing device. And with the leakage comes corrosion, bearing and equipment damage, electricity consumption, and maintenance just to operate the sump pumps, and maintenance and safety issues. Okay, when it comes to axial sealing, the seals on the axial part, so that's where the sealing action occurs, just on the sealing interface. All right, mechanical seals do not require the fine filtrated water that you need with other devices, and that's because we can use silicon carbide. So what we use are materials that are very abrasion resistant, and that reduces the quality of water. So typically, if you use an RSC or silicon carbide, your filtration goes from like 5 to 10 microns to 250 microns. All right, so there's a major difference in terms of the filtration requirements using this technology versus legacy materials. And we mentioned the carbide face materials. All right, faces are not segmented, so they are actually, the pieces are made in one piece and we split them. So basically, you don't have the leak paths that you have with all the other types of technology. The other thing that we can do is that we can keep the faces very flat because they're made in one piece. We can lap the faces to helium light bands, so that leakage through the faces is going to be minimized, and that's how we can seal without any type of leakage. All right, so they are designed to be leak-free. We mentioned before that you will get some leakage predicated on how you install it and the equipment type, but the leakage is drops per minute versus 4.2 gallons a year. All right. What we also do is that we design the faces and we balance the seal face so that the pressure on the faces are balanced, so we're not exerting a lot of heat between the faces, which makes the seal reliability improve. But we also look at how they run, and we design the shape of the seals so that we maintain the faces closed and flat, all right, during temperature gradients. All right, so the design of your seal faces will improve the the reliability and the leakage reduction that you're looking for. Okay, silicon carbide has a more value of 9. All right, diamond is 10. So typically when you have glacier water or whatever, your quartz materials, you're running around a 7. So by using materials that have abrasion resistivity to the contaminants that you're going to see, you improve your sealing reliability. All right, so the advantages of axial sealing are that you get no shaft damage, that there is reduced leakage, zero leakage. There's no maintenance to the thing. So all we want to do when we put in a seal, people say, well, what's the maintenance? We want to keep them cool and lubricated. We want to just lubricate the face. We want water on the faces. And your filtration requirements are considerably less. All right, so this is how a mechanical seal will work. So what we try to do is that we put a restriction bushing or some type of device here so that we can minimize the flow from the seal to the runner area. That way we can reduce the amount of flush that you need. We actually do calculations on heat generation based on the size of the seal and the speed of the shaft, and we'll understand what type of cooling we need for the seal. We need filtered flush water, okay, at the level. That's where the sealant interface occurs. So we have the filtered water. We push the water in. We reduce the flow with the bushing. We need the flush pressure to be greater than the runner pressure. If the runner pressure is greater than the flush pressure, the river water is forced into the stuffing box, just like the last time, but the faces are made out of silicon carbide, which resists, and they're flat. So they're designed to stay flat. So we're able to keep the seals flat so that the solids don't go through the faces, but it's also abrasion resistant, so that we can, have situations where we can run the seal when you have, off filtration, and you're okay. So it mitigates the seal damage. So you saw that picture again with the water. You need environmental controls to enhance your reliability of your sealing device. So your typical environmental control is a flush, and your flush pressure has to be greater than the runner pressure. You have self-cleaning filters, and that's going to reduce the pressure during cycling. What we see is that, that's the time when a lot of people have their issues with, solids getting into the sealing device. We mentioned all this before. Your facility locations are typically remote. High flush throughput requires large filtration capital expense and maintenance. So a lot of times what we see is that we see issues with the filtration devices and being able to run that 24/7 over time. So if you lose your system, it equates to a seal failure. With the silicon carbide, we can mitigate a lot of those issues. So, here's a seal water filtration system in a plant. All right, very complicated. You got your filters, your strainers, and all the gauges, etc. You need to get water to the system, and it's got to meet whatever requirement of the seal. So in terms of that, we understand that. We look at ways to minimize your flush requirement. All right, so the middle one we show a bushing. So what we're doing is that we're sealing the runner area so that you don't need as much water. Another device that we have is a spiral track. And basically what that does is that acts as a separator. And what we can do is that we install the spiral track into the seal area, and what it does is that it uses the centrifugal force of the shaft movement to expel particulate outside of the sealing area. So if your filtration wasn't great, or if you had high solids content, we can use this type of device to enhance the sealing reliability. And it's basically just a static bushing. Okay, we have a case history here. Just want to show you, a few actual examples of what we did. Here's the parameters of it, and I'm not going to go through that. You can see the filtration device on the back side of it. Typically, what you're looking for is you want to reduce seal leakage. Here, the position of the seal was so far into the turbine that it was unsafe to make packing adjustments, etc. So they were concerned with safety issues and turning the turbine down to make adjustments, etc. You have the collateral damage with the leakage, as you can see in the top picture. They had concerns over river water contamination. and they wanted to increase their seal reliability. So basically what they had was that they had packing, okay, which is on the left side. So we took the configuration that they had there and went to the right side. So, you know, the seal actually sits on top, all right, of the pusher plate. So there's no type of equipment modification. What we'll do is that we'll make a plate that fits your equipment and fits the seal. Again, we'll use some type of device here to minimize the flush requirement. All right, so we don't want to just push clean flush water, you know, through the sealing device and into your runner operation. Okay, so the seal ran for 3 years totally leak-free, and because they had a runner problem, we had to take the seal off. And you know, we talked to the people there, and in the entire 3-year period, they didn't have to use sump pumps at all. So there was no use of any type of you know, evacuation of leakage. All right, they know that they had flush water disrupts, and we could tell that by looking at the seal. So one of the things we wanted to do is that we wanted to you know, take a look at it and see the effect of the, you know, materials on it, and then we reinstalled the seal. So basically what we did is that we looked at the wear path. So that's the actual sealant area of the face, all right, the sealant interface. And we could look at it and we could tell, you know, how the seal was operating. So that's a piece of silicon carbide. And then we do a tracer. So we run it and we look at, you know, what's happening, say, within the sealant system. So after 3 years, there was no wear to the seal face. Okay, the noise that you see is where we had issues with bearings starting to go. All right, so very successful, 3 years, no, you know, no leakage and no use of external equipment. This example here. These people had a real horrible situation. They actually went through about 45 seals in the first year of operation. All right, due to the quality of the river water, they had a lot of glacial content, and they were losing seals, you know, daily. All right, so when we go up there now, you know, they said they tell me that all they did was repair seals. They had no opportunity to do any other maintenance work except for keeping these turbines running. And basically, this is the configuration. All right, so we have 9 of these seals in it. It's a horizontal unit, 480 millimeter shaft size, silicon carbide, and they're running for almost 2 years leak-free. All right, and that's a close-up of the picture. This is the sister unit. All right, they were so happy with the results of the 9 seals that they did 3 more, and we installed these, you know, fairly recently, maybe about 4 or 5 months ago. And here's the seal. All right, so we were able to put 3 of these seals in 2 days. All right, and make it totally operational. Some of the things that we find, if you look at the bottom of the seal here, you see this valve that typically you have a leakage containment pipe or, you know, convention to take the leakage out, and they put one on our seal. And I told them, I said, you don't need that. All right, so you can see that the handle is closed, and you know, there's no leakage. I have a little video clip. And if you can see, there's absolutely no leakage. So, you know, 2 of the 3 seals had not a drop of leakage here, all right? And the other one just had some, the first seal we put in had a minor leakage, and hopefully it's dried up by now. All right, and, you know, it's another view of the seal. As you can see on the bottom, this is where they used to hook up the seal for their leakage. The electrician, once we put these seals in, this is the place where you had that pump that was shooting water into the river. He said to me, even though they could control the leakage and they could pump it out, he goes, hey, thanks. You know, I was always afraid to go in that area where the water was because, you know, the electrical shock, you know, aspect of it. And he said, you made my life much easier to do my work. And that was one of the comments that he got. So we're a little over. I rushed through this because we only had a half hour. I apologize for that. If you have any questions, we'll take them now.
We do have a question that's been typed in. What shaft size limit for the application, if there is one?
Okay. At this moment, the shaft size limit is 39 inches. All right, so about 940 millimeters. That would be the limit of, break in the face. So the limit to the technology is the creation of the silicon carbide rings of that size. We're looking at other technologies to enhance on what's available for larger turbines, but we're not there just yet.
Thank you.
Any other questions? If you do have a question, or if you want to get in contact with me, I have my email address there. It's john.souser@chesterton.com. Feel free to email me at any time. I'll get back to you. I thank you for joining us. I know this is a lot of information for a half hour. So, I hope I didn't rush it too much. We will be doing this over again, I hope. And if you have any questions, please feel free to email me. Thank you very much.